in the past, in order for us to work out the area underneath a curve, let's say f of x equals x squared, we would have to use Riemann's sum. We would have to split this up into n number of pieces, and then it was blah 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 blah, and then that would then take us to here, and then we would, well, in order for us to use Riemann's sum, we would rely heavily on the fact that this equals this, and then we also relied on we relied heavily on this being equal to this. You see, in order for us to use Riemann's sum for x squared, we would rely heavily on this and this, and don't forget, this and this required a lot of work in order for us to develop that this equals this thing here. And then, well, in order for us to use Riemann's sum, we would need to rely heavily on this. We would need to rely heavily on the fact that this equals this and this equals this. Well, suppose we want to work out the area underneath, let's say f of x equals 1 over x. Let's say this area here from A here to B here. Then in order for us to use Riemann's sum, we might have to develop a formula that would take us from here to well, if you look back up here, we relied heavily on this being equal to this. It took us a lot of work to develop that this equals this thing here. Well, suppose we want to find out the area underneath. Let's say sine of x. So let's say we want to work out the area of one hump of sine of x here. Then using Riemann's sum, we would have to get, so this here is 0 here, and this here is pi. We would have to get pi. We would have to get this length here, which would be pi take away 0. Pi take away 0, and then cut up into n number of pieces. So delta x would be this. So in order for us to use Riemann's sum, we would have to do this. We would have to split up into n number of strips here. Okay, and then we would follow our normal routine. So the area equals, sorry, the area is approximately, hang on, is approximately, bear with me, is approximately, hang on, bear with me, is approximately, hang on, bear with me, is approximately this. So we would well, the area would be approximately this whole thing here, and then this simplifies to this, and then this here is a constant, so we would take it out. But then we would need to develop a formula for this. How would you see up here? Well, when we were trying to evaluate the area underneath x squared, y equals x squared, or f of x equals x squared, we knew this. This here allowed us to work out the area underneath f of x equals x squared. Well, when it comes to sine of x, we would need the equivalent of this thing here. So how would we go about? Well, luckily we have the fundamental theorem of calculus. So luckily someone realized that in order for us to work out the area, in order for us to work out this area here, all we need to do is integrate the function here. So hang on. Luckily, well, normally in order for us to use Riemann's sum, we would have to develop a way of evaluating this. We would need a formula to evaluate this, but luckily someone realized that in order for you to work out the area, underneath this, so the area underneath this is really, this here is A and this here is B. So this area here can be written as this. So what this is saying, so don't forget the area here can be written as this. So when you see this thing here, you will know that it's the area here. Okay, so the area here, in which case this here will be pi, because this here is pi, and this here is 0 here, so this here is 0 here. So the area underneath this one hump here would be from pi, from 0 to pi here. So the area of this hump here is simply us integrating this function here, for us to integrate this here, because it's saying if if so when you read this statement here, you're looking for you're looking for a function where when you differentiate it, it will give you this thing here. Okay, so basically it's saying that the area underneath this hump here is you trying to integrate this thing here, because capital F is the integral of this thing here. By looking at this statement, it says that. So by looking at this statement here, it's really you looking for a function capital F of x, so that when you differentiate it, it will give you our current function here. So hang on. So the area of the hump here is simply us working out the so this area here is given by us integrating this. So when you integrate this, it will give you minus cos of x. That will then give you this. So when you get to this stage here, it will be this, which is this bit here, take away, and then it will be this. Okay, so it's really us putting the pi into here, so that will then give you this, and then take away, and then us putting this into here, so that will then give you this. So from here we would get to here, and then cos of pi. If you look at the cos graph, so the cos graph looks like this. So this here is 2 pi. This here is pi. Okay, so cos of pi is -1 here. It's -1. So what's in this box here will be a -1. Okay, so what's in this box here is a -1. And then when you look at this here, cos of 0, well 0 is here. Cos of 0 will be +1. So this box here will be +1. So that's this box here. Okay, so this box here will become -1. This box here will become +1, and then blah blah blah. This thing here will be a 1, and then well blah blah blah. So it's really 1 plus 1. So the area here is 2. Okay, so the area of this here is 2. Okay.